Hi, I'm Grace Wesson, and this is the AP Calculus BC 2008 free response question number 6. Here's the initial problem. You're given a slope field, a differential equation, and an initial condition. From that, you're supposed to sketch solution curves, use Euler's method twice, and write a Taylor polynomial expansion. Here's a quick preview and some important things to remember before we start the problem. I'll also go into more depth on these later. Important skills for part A are knowing just how logistic differential equations work and how the logistic differential equation we were given maps onto this and onto the given slope field. It's really easy to forget this formula right here, dp over dt equals kp, 1 minus p over k. In this example, the big K here is the carrying capacity or the horizontal asymptote, which is very important when you are doing your slope field. Be sure you know what a slope field is too. They're typically but not always used for differential equations, and each line on the graph is essentially the tangent line at that point. Next, in the given problem, we are also instructed to use Euler's method twice to estimate f of 1 starting from f of 0. This is different from step size, which tells you what the change in x is between the values you're using, whereas using the method a certain number of times as we're given in this problem means that you divide the given interval by the number of times you'll be using Euler's method. So our given interval is 0 to 1, and since we're instructed to use it twice, we divide that interval by 2. Also, what we're given here is not the original function, but the differential equation. So when you're using Euler's, you'll need to start by finding your estimation for the y value and then plugging it into the differential equation to get your slope so you can write a tangent line. Next, you'll need to apply your knowledge of the Taylor polynomial formula to write out the second degree and general term for f of x using the initial condition and the differential equation. Lastly, you'll need to analyze the graphs that you created in part A through the point y of 0 equals 8 to find the range. All right, on to part A. I encourage you to pause this video and try it on your own. Here's the first method that was mentioned in the text on the last slide. So basically, you can start at the points that they already gave you here and then follow these slope lines up because the flatter the slope lines, the flatter the graph. So both lines will approach a slope of 0 at y equals 6, and on this line right here, it's also going to approach 0. The slope is also going to approach 0 at y equals 0. And the slope field there is all just worth 1 point. All right, here's another possible solution that you could have for part A. They all basically lead to the same answer, so either way is valid. In this one, you can use the given differential equation to find out where this horizontal asymptote is. I mean, most of the time it would be way more efficient to just look at the graph and see, oh, the slopes converge to 0 at that point, so that's probably where the horizontal asymptote is. But if you just wanted to check your work or make absolute sure, or if you have extra time, this would be a great way to do it. And then you'll know that these that's the carrying capacity, so they're all going to approach that point as the time goes on. Now in this problem, you'll be using Euler's method to approximate f of 1. Go ahead and try this one on your own. Keep in mind that since you're using Euler's method twice, starting at t of 0 and going to t equals 1, your interval is from 0 to 1 here. Since you'll be using Euler's twice, divide the interval by 2 to get your step size. So the three x values you'll be using in this interval are 0, 1/2, and 1. Starting at 0, you first need to plug in the y value you were given into the differential equation, like we're doing right here, to find the slope of the tangent line at that point, or f prime of 0. Then plug the point 0, 8 and the slope -2 into the point slope formula to get your tangent line. Next, estimate the y value for x equals 1/2 using the tangent line for t equals 0. So basically just plug the 1/2 into this tangent line. And once you have this estimated y value, you can then plug that into the differential equation to get an estimate for the slope. Now once again, you need to find the y value first before you can find the slope because the differential equation depends on y. And then once again, you're going to use the point slope formula to find the tangent line here. And then finally, you're at the last step. Plug x equals 1 into the tangent line that you just created, and there you have it. So here's some tricky things to watch out for in this problem. It's really easy to drop negative signs like this here when you're creating your tangent lines. And it's really easy to make arithmetic mistakes, so make sure you're double checking your work. Additionally, doing Euler's method at x equals 1/2 can be tricky because you need to calculate the next y value, like we did here, before finding the slope, because the differential equation is in terms of y. So it's 1 point for all of this work here, and then 1 point for the final answer. Next, we'll be writing and then using a Taylor polynomial representation of f of t. Once again, pause this and try on your own. First, be sure that you recall the general Taylor series formula, which is the sum from 0 to infinity of f to the nth derivative of a times x minus a to the n over n factorial. In this case, your a value, which is the value that it's centered around, right? So about t equals 0 means that it's just centered around t equals 0, and that means that that's your a value, or your x sub 0 power, like we used in the last slide. So your a value here is going to be 0. So from that we know that each term is just going to be the nth derivative of 0 times x to the n over n factorial. From this we know that the second degree term will be at n equals 2. So to get the answer we need the second derivative of f of t. Don't forget what you're given. We already have the 0th derivative, the initial condition of f of 0 equals 8, and the first derivative, because we have that given differential equation, and all we have to do is plug in 0. All we have to do is plug in 8. First, implicitly differentiate the differential equation that you are given. Note that you don't really need to simplify d squared y over dt squared. You don't have to substitute in the given differential equation for dy over dt here, because you're already going to be calculating that value in this step. To find the nth derivative, it helps me to make a chart like this, but it's ultimately up to you. These derivatives over n factorial are the coefficients for x to the n, as you can see from the finished Taylor polynomial. So finding your d squared y over dt squared value is 2 points here. The finished Taylor polynomial is 1 point, and then plugging in f of 1 at the end is another point. All right. So last but not least, here's part D. Part D asks you to find the range of the function when t is positive. Pause and see if you can get it. Okay, so given the initial condition of f of 0 equals 8, you can see from the slope field that f is a decreasing function on the interval with this initial condition. And it will continue to approach, but it will never touch y equals 6, the horizontal asymptote. Therefore, the range, or the interval of y values covered by this function, is from 6 here to 8. And now that's going to be there's going to be a line under this less than sign, and then no line under this one. So therefore, the range or interval of y values covered by the function is from 6 to 8, and you absolutely must distinguish between the less than sign and the less than or equal to sign.